So this video is still on the irreducibility tests, mode P irreducibility test. So we just saw an example of this mode P irreducibility test. We saw in the previous video this example of f of x, and we took f bar of x over z2, and we saw that f bar is irreducible over z2, so we immediately conclude that through the mode P test, f of x is irreducible over the rationals. Okay, in this video we're going to see another example. We have this polynomial f of x, 3/7 of x to the power of 4 minus 2/7 x to the power of 2 plus 9 over 35x plus 35. And we are going to prove that this polynomial is, we want to prove that this polynomial is irreducible over the rationals. Okay, so I'm going to get, first step, I'm going to get f of x. I'm going to build a new polynomial where I'm going to multiply f of x by 35. Okay, so I'm getting 15x to the power of 4 minus 10x to the power of 2 plus 9x plus 21. So I got h of x from f of x multiplying by 35. Okay, so I can say that the polynomial f of x is irreducible over the rationals if and only if hx, now built it with integers, right, is irreducible over the integers. But what we are going to do here is we are going to apply module 2 irreducibility test to hx. Okay, so we are going to get a h bar x. So in z2, right, since we are doing module 2 over z2, x bar is going to be x to the power of 4 plus x plus 1. Okay, and we see that in the ring of polynomials of z2, h bar has no roots in z2. H bar has no roots. You can check that. H bar has no roots in z2. No roots and no quadratic factor. If you want to check if there is no quadratic factor, you just try to divide x squared plus x plus 1. You divide that by x squared plus 1. Okay, and you see that there is no factor here. So if you divide, we see that x squared plus x plus 1 is not a factor, and x squared plus 1 cannot be factor because it has a root and h bar has no root. So we can say that h bar x is irreducible over the ring of polynomials over z2. So this guarantees that h of x is irreducible over the rationals. What I meant here is if this one had any factor, it should be either this one or this one, right? And you can divide this one by either this one or this one and check that there is none of them is a factor. Okay, so we are going to see another example. We have a polynomial f of x to the power of 5 plus 2x plus 4, and it's obvious that the theorem, the reducibility test for degrees 2 and 3 here, it doesn't work, okay? But the module P, module 2, the module 2 test, this is so handy, so quick, so simple, but it doesn't work here too, okay? Because module 2, we are not going to get a polynomial with the same degree. So the best thing is to go to our last theorem, the irreducibility test. But we have to change the P here, okay? So let us change, for instance, for mode 3. Okay, so we have these elements 0, 1 and 2, and we want to find a f of x that is equal to f bar of x. So if we put here 0 or 1 or 2, we are not getting zeros, okay? So there are no linear factors here. But f bar of x might have a quadratic factor, okay? It might have a quadratic factor. If f bar of x has a quadratic factor, it will be in this form, right? X squared plus ax plus b. Okay, so if you look well, we have 9 possibilities, okay? Because we can put 0 here and 0 here, 0 here and 1 here, 2 here and 0 here, okay? So we have 3 times 3 possibilities. We have 9 possibilities here. We have 9 different second degree polynomials possible, module 3. But we know that f bar of x cannot have a 0, right? So we immediately rule out all polynomials that give us zeros, okay? And you just do it's simple calculations, okay? So 6 of them will disappear immediately. So all we have left is x squared plus 1, x squared where this is 0 and this is 1, or this is 1 and this is 1, sorry, this is 1 and this is 2, the second one, and the third one is 2, 2. Okay, here we don't get zeros, okay? So we only have to check these 3. Okay, just perform long division here, and if you do that, you will see that not possible, not possible, not possible, okay? So we can say that f bar is irreducible over z3, so that implies that f of x is irreducible over the rationals. It's pretty obvious that it is totally unnecessary to check for cubic or fourth degrees here. For cubic or fourth degree factors, that's totally useless.